Thank you so much for the kind introduction. Thank you everyone for being here. I see some familiar faces in the crowd, mainly from my own lab, but let's change that and I can get to know the rest of you as well. So indeed, I'm coming from the Civil and Environmental Engineering department, and here's my team. We took this picture a couple of weeks ago, and you can see most of my students actually do not have a civil and environmental engineering background, but they're actually roboticists and computer scientists, and we are working to solve problems that exist in the building industry, but we use computer vision for that. And in general, the kind of work that my group does is about understanding what exists in a space, how it was constructed, and how it changes over time, with the ultimate goal of creating sustainable, inclusive, and adaptive built environments that place the human in the center and take also into account our current and future physical and digital needs as well. And although this is a little bit further from what robotics is doing, we are also thinking about how can we be at the interface of physical and digital, for example, with immersive technologies, VR and AR, and how we can create actually and design spaces, physical spaces, that allow this interaction between the physical world and the virtual world. And we call those gradient realities, and that's how the name of the lab came up, Gradient Spaces. Now, today, I will specifically talk about how can we create and update digital replicas or evolving representations of our indoor scenes as they change over time. And we're calling those living scenes. Now, we can make the comparison that buildings are like living organisms, which means they evolve over time. So how can we realistically maintain and update their representations throughout their lifespan? So we have agents that exist in the wild, and as they do that, they can navigate within existing environments, they can act within them, or interact with them. And in order to do all of these, they need to be able to map and understand their surrounding environment. So you can see here, for example, a demonstration I found online, and imagine that all those little gray dots are agents, one or multiple agents that operate within the environment at different times. So they have different trajectories, they collect different data with changes within them. So imagine, for example, here, if you had the agent at 2 different times exploring different parts of the environment, and you want to collect all those together. So essentially, we need to get all this different data that an agent collects while performing tasks and create those evolving representations of the indoor environment, which means we need to be able to align and merge spatiotemporal data. Now, as I just mentioned, we're not talking about acquiring data without an agent. Agent can go around and can be performing repetitive tasks within a single scene, within an environment. And as they do that, they capture information about the environment within them, probably 3D information, sometimes 2D. But imagine if we acquire all this data and create a cumulative scene understanding, scene representation over multiple of these 3D scans we acquire over multiple times, we can create a progressively improving in geometric completeness and accuracy map of our environment. Particularly if there are scenes of our, places of our scene, parts of our scene that we've never seen before in temporal time 1, but temporal time 2, when we perform a different action or something has changed, we can actually see more and more of that. And why is that important? Because in this way, we can enhance the interaction with the objects within the scene by having a more accurate geometry and more complete geometry. And we can start having a foundational understanding of how objects move within the scene. And with that, I will touch upon 3 works that look into creating and updating replicas of geometry and semantics using visual data that agents acquire while performing tasks. And that by thinking of realistic implementations and also privacy preserving in certain cases. And so we'll look at geometry-based, scene graph-based, and at a work that looks at drastic change. And before I even go into understanding living representations and changing representations, let's focus on how can we acquire it at one temporal point. And there are very different methods that you can do that, but I will focus on 2 works that we've done in my lab. And the first one is one that is under review by Li and Zhu. It's called Loop Splat, and essentially we are using the 3D Gaussian splat representation in order to, in an online manner, reconstruct the scene with great accuracy. And the particular innovation of this method is that it's able to perform loop detection and perform loop closure by registering 3D Gaussian splats together. The trajectory, you see it on the screen, and it has different colors, and that designate how much drift it exists from the ground truth trajectory. And if you notice the video for quite a while, you will see that in certain cases, when it does detect the loop closure, the color of the trajectory changes to minimizing that drift. Another work that we've done with my student Jan Housing is about creating an adaptive real-time 3D semantic understanding of the scene. And in this particular work, we focused on that we don't need everything in anything, and that sustainability starts from the data we're collecting. So instead of collecting too much data on too high resolution without even knowing what we're going to do with it, we can actually create on one single map with adaptive quality, which means certain regions are going to be in very high fidelity. Essentially, if you consider a voxel map representation in a very small resolution, or it can also be in a very low resolution in other parts that you don't care that much about. And that can be defined by user-based semantics, by the geometric complexity of the scene, and by any other criterion you might want. Now, we've seen two works that can get you into what exists right now as you are looking at this scene. Let's look about how to do it when you have evolving environments. The first work I want to refer to actually has the same name as the talk in terms of living scenes. Again, it's from my student Lian Zhu. It was a paper in CVPR 2024 as a spotlight. Now, in this particular work, I'm going to make an even more refined definition of what it means to be a living scene. We're talking about evolving environments where you have irregular changes and of which you have sparse observations. So you might have an observation of it right now, then after maybe 2 weeks, after 1 month, so you don't know what happened in between. And the goal is, given these sparse 3D observations, can you relocalize the objects within the scene and reconstruct them on an individual object level, object instance level? So this is the method overview, where we begin by, can you actually see my pointer? Great. Where we begin by having as an input the scene at 2 temporal points where things have changed. The first step is to perform instance matching. We make the assumptions that we have instance segmentation, and actually it's a valid one because we tried both ground truth and predicted instances, and we actually are very robust to the noise as well. And so given an instance matching, we are going to register the different point clouds of each object, and then we're going to reconstruct it in order to get, over time, a more complete in geometry and accuracy point cloud of that particular, or mesh of that particular object instance. Now, the cool part of this work is that we have one representation that's able to solve all 3 tasks by utilizing different embedding spaces, and I will comment on that in a bit. It is trained only on synthetic data, so for those that are familiar with CAD models and with the ShapeNet database, we only use that for training, and we evaluated 0-shot on a real-world noisy data set. And beyond of what it sees, it is also able to reconstruct unseen parts of those objects by having, essentially doing shape completion, by understanding geometric priors of those particular categories. So behind everything, as I said, is this one representation that solves all tasks. And we're talking about a vector neuron encoder, where it gives us an equivariant and invariant feature space. And afterwards, we have a DBSDF encoder that actually gives us this ability to perform shape completion. We are category agnostic, which means we don't need to know if it's a chair, a table, or another object within the scene, but we are training on a total of 7 categories from ShapeNet. And the interesting part of the 2 embedding spaces of the equivariant and invariant is that the equivariant can give us information about the pose of the objects in the scene, and the invariant about the actual geometry and shape of it. And if we utilize them in different manners, we are able to solve all of these tasks: the matching, the reconstruction, the registration, and reconstruction. Here you can see some qualitative results on the synthetic data set, where we have stage 1, stage 2, stage 3, stage 4. You can see at the top the input point clouds, and at the bottom the reconstruction of the objects after doing the accumulated living scenes method. You see here, for example, you can see with the orange we track the chair, with the red we track the table, and you see also how they look quite completed when you look at the reconstruction. As I said, we also evaluate zero-shot on a real-world dataset. It is a 3R scan dataset. This particular dataset has many reconstructed scenes that have been visited multiple times throughout their use from humans, and they include essentially these temporal changes. Here are some qualitative results, where this is temporal time 1, 2, and 3. You can see that we have objects moving around or even being removed from the scene. And here is what the baseline and hours are able to perform. And you see how we are actually getting very close to representing the geometry and the completion of the object. Here is another example at 3 different temporal points. And again, we outperform the baseline. One would say, well, what is the benefit of accumulation? You tell us that it's actually able to do probably better in completeness and accuracy, but is it true? And yes, it is. We performed an experiment where we have different point clouds from different viewpoints every time of the same object. And the more you see of that object, the more you're able to reconstruct its geometry and its completeness. And actually, we're able to minimize registration error and maximize reconstruction accuracy by having these multiple viewpoints from different temporal times. Now, this was about the geometry-based way to have this evolving indoor representation. So the second one is about scene graphs. Maybe some of you are familiar with this representation, but I will explain it in a second. This is a work done by my student, Cheyenne. It was submitted in ICCV, which was it? 2023. Okay, thanks. Okay, so when we build a map, we can actually do it in a low-level manner, which means we're going to have representations such as occupancy maps, voxel grids, octomaps, hash grids, etc., point clouds, and different other representations. However, there are some issues with those. The decision-making takes place on the metric space, which means directly on 1 centimeter to the left, we have a chair, and we expect in another scene, if we're going to generalize the chair to be 1 centimeter to the left, right? Which means that the semantic labels are attached directly on the geometry, on the voxels. And that limits a higher level understanding that it has been shown in certain robotic works that it actually minimizes the generalization to variance in scenes, because again, you are looking into the centimeters instead of that object is usually found next to that object. On the other hand, if you go building a map in a higher level, you can use 3D scene graphs, where essentially you can have both high-level and low-level information, which means you can still have your voxels if you want them. And it allows for decision-making on a more abstract space, on the semantic space. It is lightweight, and it is privacy-preserving. Good. Now, 3D scene graphs are used a lot and increasingly in agents in order to build in the fly, either to build them on the fly, to perform robotic navigation or task completion. And there are several works that utilize scene graphs, which means it is actually a representation that a lot of robotics agents are already benefiting from and using. And you can also predict them in an online incremental manner or in an offline manner if you want it. So our goal here is, can we leverage the information that the agents are already building in the background in order to create 3D maps of the environments? And we are talking about maps that are either, we have scene observations from one or multiple agents, we have static or changed scenes, and we have overlaps from 0 to partial to full between all of the scenes, and we are able to robustly identify how to stitch the maps together. Here is how SGLiner works. I show here the point cloud, where exactly the input to our scene is a scene graph. In this case, it's a very abstracted and rudimentary scene graph for the purposes of visualization, because otherwise it's a very complex graph to show on a screen. And you can see here that these two actually point clouds have some overlap between them, very little. Actually, it must be only the chair in this particular case. And we want to stitch those two together. So the SGLiner will take the graphs. It will essentially perform node matching in order to identify how these two graphs are aligning together, and that is a great initialization to perform a task such as point cloud registration or point cloud mosaicing. why do we want to do that? And why don't we just use existing methods for point cloud registration, where the issue with them is that they are focusing a lot on local feature descriptors. And so if there are changes in the scene or very low overlap, they are going to have issues with being able to perform the alignment. They are not as robust to point cloud density, to the spatial extent of the overlap and of the entire scene. Though it's a very large scene, they're going to have issues being able to compute all that in a pass forward. They are not, as I said, robust to change. They assume that you have partial overlap between your scenes, and so if you have no overlap, they kind of fail to understand that, etc. Now, we form this SG aligner, the alignment of scene graphs, as seeing them as multimodal knowledge graphs, because they have three types of information within them, the scene graphs: semantic entities in the scene, which means the object instances. You have attributes for them, such as the category, the size, maybe the material of the object, and you also know relationships between these entities, such as their relative position or some kind of attribute similarity, and more. And so we can redesign entity alignment methods from the multi-knowledge graph, multimodal knowledge graph domain into our setting, which is to align spatial maps together. Looking into multimodal knowledge graph alignment, their goal is to align multiple knowledge graphs that represent information with different input modalities. So we're talking about text, images, video, whatever else you have, and integrate all this knowledge from different sources in order to create this better understanding and cumulative understanding of your space, of the world. However, please note that all the works that look into entity alignment, multimodal knowledge graph alignment, consider that their inputs are overlapping in information, and all the information they have within them, it is actually true, which is not the case when you're looking into using 3D scene graphs that the agents are building on the fly, because you cannot assume that there always will be overlap. And in addition to that, they're going to have, since it's a predicted scene graph, it's going to have errors, right? So we cannot assume that we have perfect input. In more details, this is how SG Aligner looks like. So given the 3D scene graphs as an input, we have unimodal embeddings that's going to take each of the modality information separately to encode it. And so we have point cloud encoders that's going to understand more about the shape and the category. We're going to have structure encoders that's going to look into the layout of objects and their in-between relationships. And then we're going to have some meta-encoders that encode attributes or relative relationships between objects. And all of these are going to interact in a joint embedding space, where we want to be seeing the same object instance to come closer together and object instances that are not the same to be further apart. And then with that information, we can align the 3D scene graphs and be able to perform tasks such as pretty point cloud registration. We used, again, the 3R scan dataset I explained before, as well as its extension, the 3D SSG, which provides 3D scene graphs for each of those changed scenes. The very first task that we evaluated with the SG Aligner is, can we actually match nodes together? And I don't want you to focus on specifically the numbers, but let me tell you that regardless of whether you use ground truth information or predicted scene graph information, you're actually doing very robustly. So we have a very small decrease in our numbers, in our performance if we use predicted scene graphs. In addition, in varying overlap conditions, especially in the very low overlap region of 10 to 30% of spatial overlap of point clouds, we're actually seeing that we are extremely robust as well, something that usual 3D point cloud registration methods fail to achieve. And finally, even if you have temporal changes within your scene graphs, you're still able to perform very, very well in the alignment. And again, this is node matching. Can we match two nodes together with the one that it's supposed to be matched with? Looking into 3D scene graph alignment, we want to see, okay, we matched some nodes. Can we still be able to figure out whether these align together and how they're aligning? And again, the answer is yes, we can do that. And in this particular scenario, we consider if we have the top two matched nodes, the 50% of the nodes matched or all nodes matched, what is the performance? And we get the best one when at least two nodes are matched for these particular scene graphs. And now we use this information in order to perform 3D point cloud registration. And in contrast to previous approaches, to common approaches, where they take the 2-point clouds, imagine that the red triangle is one scene point cloud, the green triangle is another scene point cloud that have some overlap between them. And they're going to process them to get local features, get some kind of embedding information, use RANSAC, baby ICP, and be able to perform the final geometric alignment between them. In our particular scenario, since we know which object instances are matched with the others, and hopefully correctly, we're gonna calculate the registration between object instances. So we're essentially registering object instances instead of entire scenes. And once we are able to register each individual object instance together, we're gonna utilize this information in order to align the entire scene in a more robust way, and actually in a faster way. And so again, without focusing in the large table, I'm going to tell you that we have 49% improvement in chaff per distance, a standard registration metric, and about 40% improvement in relative translation error. And we have even higher gains with respect to other methods if we look at noisy point cloud predictions, which again is the realistic scenario to consider. Also in varying overlap, we're doing very well. So in cases of 10 to 30% low overlap, we're still able to handle with very good results the task. The final thing that we tried is what I mentioned at the very beginning of this work, where I said we can have scenes that are overlapping from 0 to partial to fully. And why fully? Because sometimes if you have temporal changes, or if you capture your scene, even if it's the same and nothing has changed over time, you may capture a smaller part of it, right? So maybe you have full overlap with the previous scene. However, in the 0-case scenario, 0 overlap, it means that you might have, in your folder, a bunch of different point clouds that you don't know how to stitch them together. And previous methods are not able to perform that robustly in understanding, does these two point clouds overlap or not? And actually, in our case, we can very well understand that 3 times faster than prior art, which when you have a robotics platform going around, you want to do that as fast as possible. And we're able to identify the overlapping pairs more correctly. Now, I told you about the geometry-based alignments. I told you about the scene graph-based alignments. But all of them look at a scene that evolves with minimum changes in geometry. What I mean by that, we just have some furniture being relocated or something being added or removed from the scene. But what happens when there are more drastic changes in the scene? And I will talk about our work, Nothing Stands Still, that my student Tao San has performed. Now, we're talking about spatiotemporal 3D point cloud registration in this particular case, where essentially we want to be able to find pairwise correspondences from the static parts of the scene and hopefully exclude the temporal changes because they're not going to help us to align the geometries together. Now, looking into prior work, you're going to see that in terms of spatiotemporal 3D point cloud datasets, we are looking into datasets that have very small scale scenes, maybe up to a room, that the change type is that of the relocation, addition, or removal of furniture from the scene. And also they capture just standard daily human interaction activities with their relocation of objects, which is fine. However, it doesn't capture the drastic changes. And if we look at methods that do 3D point cloud spatiotemporal registration, they are only able to handle small changes in the geometry of the scene, such as you would find in self-driving car scenarios, where most of the scene is static, like the buildings are there, the road is there, it will not change in the next couple of seconds, and you're going to capture your next point cloud. The only thing that would have moved is a car in front of you, a bicyclist maybe appears, and a pedestrian disappears. Okay, so can existing methods perform robustly on environments that underwent large changes? And can any of you tell me of one particular scenario where we do encounter large, drastic changes in the world in a small amount of time, relatively? Anybody? Maybe my background might, or the department I belong to might be able to give you a hint. Yes?
Construction sites?
Yes, construction sites. Perfect. Okay, here you can see a construction site where in a very short amount of time, you're going to have things added. The geometry is going to change. The appearance is going to change. The topology is going to change. And not only very local in the scene, but the entire scene is going to have that. And so that is why we created Nothing Stands Still, which more than anything at this point is a benchmark about giving this new data set to the world and benchmarking existing spatiotemporal point cloud registration methods to see and answer the question, can existing methods be able to perform this task on these particular scenes? And so we collected data from different construction sites over time, where we went with a tripod-based device in order to collect the scene at one temporal point. And then we were talking to the contractor, where should we go again? We want to capture information before it gets hidden behind surfaces, such as we would like to know the pipes behind this wall surface over here. And then we capture more and more, and we have all these little red dots and all these little seams that we want somehow to align spatiotemporally together. And this becomes easier as is a more trivial problem to be able to align things if we put them in the same coordinate system, like to understand what has changed. But it's not very easy to perform because we're talking about these very large changes in the scenes and we have areas that are inconsistently captured over time. Some parts may be inaccessible for us, etc. And so there are several difficulties to make that happen. And this is the benchmark that we created, where essentially we're going to be able to evaluate on both pairwise registration and multi-way registration of the scene, because we're talking about very large scenes. And in order to do that, we capture, as I said, a data set over 6 construction sites over several months. And particularly, we focused on interior layout construction. So you're not going to find a foundation on our excavators of this particular data set right now, maybe in the future. So essentially, we have the slabs, we have the ceilings, we have the walls outside. We're just inside have a big empty space that we want to fill. Here are some snapshots of how the interiors look like. So you start with a big empty space and you start adding all the little walls, you start insulations, pipes, air ducts, materials are all hovering around, and you want to be able, given these very drastically changed environments, to perform the spatiotemporal registration. What is also very challenging in these sites is that in addition to have drastic changes, they have very repetitive elements that look similar to each other. So we have the little studs that are going to be inside your wall. They're like essentially some kind of vertical little structural columns almost that are going to be one next to each other, maybe some inches apart. So when, as a registration algorithm, you're trying to match these things together, you don't know which stud corresponds to which stud because they all look the same. Also, appearance-wise, we're talking about a very uniformly-looking environment. Most of it is gray or brown, very little is standing out. So how can you perform this task in a robust manner? Here are some more visuals of this particular data set that you can see. We maybe, for example, over here in the blue case, we have the interior layout getting constructed. And as we go to the yellow phase, we see that everything is being done and even the static furniture is being built and nicely finished. And in the other case, we start from almost nothing to actually having the final static furniture. Here are some explorations of the meshes in virtual reality, where you can see how spaces change over time, and you can maybe understand a bit more the complexity of these things. And so we performed pairwise registration, where we evaluated existing methods in a way that you can see on the screen. Essentially, those methods usually take 2 small point clouds as an input that have some spatial overlap, and you perform correspondence estimation, and then ransack maybe some ICP at the end in order to perform the final understand the final transformation between them. And then we also evaluated on multi-way registration, where essentially we're talking about having a pose graph of all the little point clouds over space and time, and we are going to connect them with edges as long as we have a pairwise registration result, and we're going to try to minimize the weighted RMSE for those of the poses of the pose graph. I'm not going to bore you with results. I'm going to tell you that almost no method today can actually handle that. We've developed recently one that is doing better, but I don't include the results here for that. I want to show you just what happens before and after multi-way registration for the best performing algorithm at the time we benchmarked everything. And you can see that before multi-way, everything is a little bit of a blur. And after multi-way, we can actually start seeing the shaft over here in the building where usually pipes and elevators go through, and a little bit better organization, but still a lot of failures. FYI, colors being different temporal points. So whatever is cyan is one temporal point, red is another, yellow is another, etc. So bottom line, we need better algorithms to perform this kind of tasks and understand the large, drastic changes in the environment. And our assumption and hypothesis is that if we're able to solve this very hard problem, we can solve everything else as well. So more people should start working on this and use our data set. To conclude, we talked about how to go from static to living scenes and create and update the representations of evolving indoor scenes. And I want to show a few applications. Is there anyone here from civil and environmental engineering, apart from my students? Okay, one person. Fair enough. The rest might be for you on this last slide. But I want to motivate you a little bit more why it's important to focus on the building industry and why we are working on these problems. First of all, renovation is a big scope in the architecture, engineering, and construction industry right now because we want to increase sustainability and create a circular built environment where we can reuse material from other buildings that are being demolished to new buildings that we are designing. We need to be able to extend the life of an existing building in order to not demolish it as fast as we would. And essentially, we are trying to utilize existing resources without depleting new resources from the planet. In addition, why do we need to get this representation from evolving environments is because for most of our buildings, we do not have any digital information. Actually, CAD and essentially computer-aided design software that is used usually by architects to design new buildings became more widespread after the 1980s. And maybe for your age, it's too old. You know, it's like centuries ago for you guys. However, it is still only a few buildings, a few hundreds of maybe thousands of buildings have been built since then. We have billions of buildings on Earth that date before the 1980s. So how can we acquire this and keep updating the representation over time? In addition, construction industry is extremely painfully expensive. And that is why we cannot perform good estimations about how much it costs, because we actually do not know what we're building, and everything is a very visual estimate of what's going on. We have 50% of construction cost to be increased to be accounted for rework. So essentially, of everything you have to pay on top of the estimate, the first estimate, the initial estimate of your work, is because you didn't build something correctly and you need to change it. I also want to mention that construction workers accounted for 20% of all occupation fatalities in 2020 in the US, and we're talking about 1,000 people not injured that really were killed in construction sites because of something that went wrong. And lastly, 90% of non-hazardous construction and demolition material is either reusable or recyclable. However, these days, it's just dropped into landfill. So I want to stress that out to motivate you to work on these kind of problems, because understanding spatiotemporal information can have a big impact on human life and on planet sustainability. So if you want to work on these kind of problems, feel free to send me an email and I'm happy to work with you. And that is that. I'm happy to take any questions.
Could you please elaborate more on examples of how to apply the model to improve circular economy and cutting down construction costs, and also you showed an example of how it's being applied in a building at a construction site, but how about potential application scenarios in taking a building down if the building is too old? Thanks.
Right. So if you have new construction, you want to be capturing the information of what exists within it, because then you know exactly what materials exist, where they have been located, how they have been connected with each other, in order to know when you're going to do the demolition or when you're planning to design a new building, what already exists that is able to be harvested. So what we're trying to do with circularity is that we're trying to plan ahead and know that at that particular time when we want to create a new building, what are potential materials that will be available? Because then you might also know that that and that and that building will be demolished or already have been demolished. And so you can harvest these materials. And so you can start designing by taking into account those specific materials, potentially changing a little bit your design to be able to use those materials as your primary source of structure. Now, in addition to be able to understand what is a new construction and how things are being placed, you also want to know how things deteriorate and what is the condition of materials. And also for those spaces where we don't have new construction, you want to essentially get the as-is status of your space right now. And you want to essentially build a map. And you want to also continue be controlling and updating that map with any deterioration on your materials. For all of these operations, you don't only need geometric information, you also need semantic information, which is something I didn't touch too much upon here, maybe a little bit, but we are also working on this kind of work in my lab. So once you have information about where things are and what they are, you can really start planning ahead on creating new buildings in a more sustainable way.
And just a follow-up question on your last several points. Would you mind be a little bit more specific on so in the knowledge graphs, what are the exact relationships each edge is representing between entities?
Yes. That depends a little bit on the definition of the scene graph you give for the tasks you may be doing. You can have varying information, and in our particular case, we used the object categories. Do you want to say actually all the information we used?
So the nodes are the objects where you represent the objects using object categories, and the relationships are like semantic and geometric relationships. So from a particular viewpoint, you can say that the table is, for example, if I'm looking from my viewpoint, the chair you are sitting in is in front of the table. So that's the relationship in front of. So usually these relationships are taken from a particular viewpoint.
And just to repeat it for those online, essentially object instances, attributes such as size, maybe material, and of course relationships that are relative relationships within the space, such as this is in front of that, to the left of that, on top of that, etc.
So thank you for the presentation. So you mentioned about the importance to avoiding rework in construction. So do we have sufficient methods to compare point cloud or 3D scene graph to existing CAD or BIM model?
Yes, that is a very good question. There is a reason why I didn't touch upon that. We're actually working on it these days. Yes and no. And I will tell you why there are issues with aligning CAD models or building information models with existing point clouds. I think 3D scene graphs would actually be more robust to be able to perform the alignment, but if you were to just do it in a geometric manner on point clouds directly, let's say you can sample points on your CAD model, there are issues of completeness. So your existing point cloud will never be as complete as the one you have in your CAD model. There are issues of scale. Your CAD model is not necessarily the same kind of scale of the world as it is in your scanned point cloud. Sometimes the level of detail is very different as well. So there are usually the designs that we do are way more abstracted than the actual physical world. So if you take all these into consideration, if you do it just geometrically, it usually fails badly. Not too bad, but still doesn't give you an accurate registration to be able to transfer semantic information from your CAD model to the point cloud to essentially be able to perform the comparison. Is this built or not? Is this the same as in the as designed or not, etc. Particularly if we're talking about construction, usually we do not have detailed building information models or CAD models at every construction step, or even with enough construction details to perform that kind of comparison. If you are talking just about at the finished building to compare it with the design of it, I think our method with 3D scene graphs would work very, very well. But no geometric method would be able to do very well on that.
Thank you.
Yeah.
Do your models infer any physics from the scene, such as whether something's brittle or whether it will fall, if it falls, it breaks, things along those lines? Or what are your views on that type of problem in general?
Yeah, we do not perform any physics here. We assume that the change has already happened and it doesn't evolve after we capture the scene, which means it reaches its final destination. And if it's something that fell, it fell. If you wanted to do that, I suppose you would need to use a physics simulator, but I would need to understand better the task that you would be referring to comment in a more appropriate way. There's that question, and then over there. I think it's for...
Okay. As a follow-up to that, can you load these scene graphs into Unreal or Unity?
I mean,
Is that the way you're displaying?
No.
No.
No. It is manually created, right? Yeah. It's a manually created scene graph over there. But you mean like once you have the scene graph, if you can load it into Unity?
Yeah.
I mean, it's a JSON file at the end of the day, right? So I suppose it is.
Well, yeah, I figured you would have already done it. So I guess the question is, I guess what you're saying is why not?
I mean, why do you want to do it in Unity? If you want it for VR, you meant for the VR part of it?
Or let's say you're doing simulations. We'll follow up on his question. You could do all simulations in Unreal or something else. Can you load it into Gazebo, right? So
Yeah. We haven't tried it, so I will make an assumption by saying yes. But it is a scene graph, and it's a JSON file, and you have the geometry, so.
You guys have these on GitHub? Some examples.
Yes, but at the end of the day, these are existing datasets that were not produced by us. I mean, the 3R scan, So you can definitely refer to that work, and 3DSSG, which is the one that provides the scene graphs, and you can then utilize the geometry and the scene graph to see if you can load it. In the construction sites, we don't have yet scene graphs. We only have 3D geometry, because it is very painful to annotate these particular scenes. We are building some tools to automate annotation on them, which I cannot refer to them more right now because it's ongoing work at the very first stages. But I'm happy to, when it's out, to send you a link if you want. Yeah. There was a question here, and I know they already made a question, but.
Oh, sorry, yeah, just quick. Could you elaborate on how can your method be potentially integrated with like Internet of Things? Like, for example, if you place like a chip on the certain objects in the environment that stores information about the materials, the dates, and the degree of deterioration and stuff. Like, how can this method be potentially taken advantage of those?
Right. We're not working that much on fusing different types of information, but visual information these days. However, I can assume, depending on the task you want to solve, that this information is very important. Yeah. You can attach it on the scene graph as an attribute, because the attributes are non-specific. You can add as many as you want. Yeah. Was a question over there?
Hi, and I really like the deconstruction part you mentioned, like using the living things. And can you please give us a detailed example how your proposed solutions can help in the deconstruction process? Like, for example, after you have the scanned model, can the workers use those information to detect which part can be reused and how to cut those reusable portions by what kind of methodologies?
Yeah. The interesting part here is that connections play a big role, connections between materials. And usually connections with glues and nails sometimes can disrupt the structure of a particular building element. These are things we are not necessarily capturing in the data that we have. We know that this is put over there. Maybe we can see if there is a specific connection that is visible from imagery, but that's that. Now, you can understand that much about deconstruction by looking into your construction, but if you don't capture that information, it becomes even harder to have, you will have a certain estimate, but it's not going to be accurate, because you never know what you're going to find afterwards. And in addition, you don't know what is the deterioration of the material behind to what is visible to you, because you don't know what's going on behind the wall 50 years or 100 years later. So you can only make assumptions.
Yeah, so how can this process enhance the deconstruction process? Like, what kind of information the workers can get from those models?
You can definitely understand what materials would exist in this building and what can be actually harvested out of that, because then you understand the size of the panels, you can understand the size of the windows, the types of air ducts that exist, how big they are. You can get a lot of information. However, at the end of the day, it will give you an initial estimate, an initial hypothesis that this building could be used. But the moment you start going for thinking about a demolition, you have to have a very accurate on-the-spot survey of what is the status of your building right now. So this approach does not mean that you don't need someone to go on the spot and survey the building after all. You do need that. But it just helps you, out of the millions of buildings that we have out there, start making some matching between what would be the best for your new design.
If it's okay, I'd like to know like a little more detail as to which sensors are required specifically for this, and like, is there a minimum? Is there a minimum resolution? How that compares to what you can currently find in like laser range finding or whatever?
Right. Are we talking about which task? Circularity?
For what?
Which task are we talking about?
For construction.
Construction?
Yes.
To do construction progress monitoring or to do the deconstruction you discussed?
I was more interested in progress monitoring, but I am curious about both.
Okay.
Because I think that also ties into inspection.
Right. So, okay. At this point, we have nothing. So even a chip sensor would be enough. A sensor that does a good job would be enough. Because we really have nothing out there. Also think that laser scanners are great, but in order to collect data on the scale of a building, you need a system that is fast, and essentially a tripod-based laser scanner that takes 5 minutes to do one rotation. It is not scalable. So you need systems that are scalable. There are backpacks who are faster and usually similarly accurate, but I'm sure they have their caveats as well in terms of the potential drift, etc., that may be happening. In addition, they capture so many millions of points that it's very hard to process information to perform construction progress monitoring. That's why, for example, a method like the adaptive reconstruction we proposed is going to be very helpful. And the reason why that would be very helpful is because when you do construction progress monitoring, you only care about the things you just installed. So you don't need to care about anything else, but you need to care about if your studs or pipes or whatever was installed at the right position at the right time, and how much of it. Imagery can also take you to a certain point forward, like multi-view imagery. It's not going to be a perfect point cloud, so sizes could be off, but at least you would know what has been installed and when, which is already a big step forward to what we have right now. So I would suggest, if you want the perfect data, a laser scanner that has adaptive reconstruction capabilities and is able to perform this in a fast iterative manner would be probably the best solution, and getting images as well, because we need images to understand materials. We cannot get that from point clouds. We need the high frequency information from the images. I know I'm not answering exactly your question, but I hope it helps.
Oh, yeah. Oh, thank you.
Yeah. Essentially, everything counts at this point, right? When you have nothing, even the smallest thing can be of big use. Any last question?
So I was wondering, when you mentioned about the material characterization for a particular object, so is it assigned manually, or we just assume that like if we are using pipes if we find pipes from the 3D scan, those pipes are made of steel or maybe PVC or something else, or are we going to manually add the data that okay, this particular pipe's used in this particular scene or made of steel?
Right. Listen, we are at the end of the day talking only about visual information. So you can detect materials on images and understand what they are. That being said, it's only what the visual information can give you, right? It may look, it's made out of silver, so maybe it's a metal, but at the end of the day it could be then ceramic and you wouldn't know because of how it looks like. So yes, with the sake of oversimplifying things, you can understand materials from imagery. And you can just have those kind of predictions to help you understand what you have on your scene. On the other hand, if you already have some documentation of your building as it was constructed, you always have some referral of what has been planned to be installed and what were the elements that were ordered, so you could make this decision easier for you by at least making sure that the element that was supposed to be installed is indeed that particular material. Mm-hmm.
Thank you.
You want one more question? Last one? Yes.
Yeah. So does the model also work in like a non-confined space? So we are seeing all the examples in, for example, like closed room area, but what if it's like top down, like an open space, like outside stuff?
Outdoor spaces, like in squares or roads or parks.
Yeah, like for example, like in parks, it's looking down at like multiple buildings, and you don't really have sort of like an ending edge around the whole space. And for example, if I want to use this model to model my city or my urban area right now, and to figure out where I can place solar panels, for example, like how would the massive scale like work in such an open space?
I mean, in an urban environment, placing solar panels, I guess, would be on roofs of buildings and not on land. But aerial kind of scanning or imagery would help you with that. Even like Google Street Maps have 3D information in certain cities, so that could take you a little bit, you can do things with that. If you want to understand how things change, our living scenes work that does instance matching. I mean, we've never tried any of those outdoor, but the one that would for sure generalize in an easier way would be the scene graph work, because it works on the semantic space. The other one, because it's restricted to actually having to be trained on certain amount of categories, then you would have to train it on certain amount of categories. One potential workaround is to consider open scene understanding in this case, which we haven't yet done, but it is a possible extension. Yeah. Good? Great.
Thanks very much.
Thank you everyone for being here.